students, in continuation to the second chapter, electrostatic potential and capacitance. Today we will discuss potential due to an electric dipole. Now, potential due to an electric dipole. Do you know electric dipole? A system of two equal and opposite charges separated by a small distance. Now, when we talk about the electric dipole, say there is a dipole minus Q and plus Q. Okay, and this is the center of the dipole. And we'll take a general point, say this is the general point. We have taken a general point and then we join these two ends of the charges like this. Okay, now this is say A and this is B. Now this is from the center of the dipole, this distance is say R, and this angle subtended is theta. And then this may be the R1 distance and this can be considered as R2. And what you do that you draw a perpendicular from this B end on this R1, and this is the say perpendicular distance. Now this gap between these two is R1 minus R2. Okay, so this is R1 minus R2. Now this is the total length of the dipole. This is 2A. This is the length of the dipole. So this is the R from the center of the dipole. This is R1 from the first charge minus Q, R2 from the second charge plus Q. Now this is a dipole and we are going to calculate a potential at general point. Now this is at a general point, not on, so we can say at a general point. Okay, so very simple, we can start it. Say V1 is the electric potential due to minus Q. Okay, and that means V1 will be what? If you calculate, V1 will be minus KQ by what? What is the distance? Is R1. Okay, and then similarly we say V2 is the electric potential due to what? Plus Q. So that will be, V2 will be what? It will be KQ by what? R2. This is positive charge. And you know the net potential will be V equal to V1 plus V2. We know that it follows additivity. So simply we'll add them and then it will be minus KQ by R1 plus KQ by what? R2. And we can even write it like KQ by R2 minus KQ by what? R1. And then KQ can be taken as common and in bracket it will be 1 upon R1 minus 1 upon R2 minus 1 upon R1. Okay, and then you can even write KQ and this will be R1 R2 and this will be R1 minus R2. Now there is a very interesting case. If point P lies what? Away from dipole, it is far away from dipole. This point P is away from dipole. Do you know in that condition what happens? That R1 minus R2, this part is what? This is theta. So this part R1 minus R2 can be written as AB what? This is AB and this can be written as AB cos theta, nearly equal to AB cos theta. This part. Okay, and R1 R2 can be written as r square, because almost r1 and r2 are same. In that case, it is far away. And then V can be written as KQ in place of R1, R2, AB cos theta. And do you know what is AB cos theta? It is written as AB cos theta by what? R square. So finally, V, what is K? 4 pi epsilon naught, 1 by 4 pi epsilon naught. AB is 2A cos theta by what? R square. And finally you write 1 upon 4 pi epsilon naught P cos theta by what? R square. So this is what? The potential due to a dipole at a point P. So this is the form which we got from here. So again repeating, this R1 minus R2 can be written as what? AB what? Cos theta. And this R1 R2 is R square. This is the general form. And very interesting is that V is inversely proportional to what? R square. Now you can take two cases from here. If you see, what you got is V equal to 1 upon 4 pi epsilon naught P cos theta by what? R square. Now what are the two special cases? Two special cases are, remember, one is axial line and one is equatorial line. When point P lies on axial line, okay, you know that minus q and then plus q, and that point P is lying on axial line. So do you know what will happen? What will be the value of theta? Theta will be what? 0, or on that side it can be what? 180. So ultimately this V will be plus minus 1 upon 4 pi epsilon naught P by what? R square. You know cos 180 is minus 1 and cos 0 is 1. If it lies on axial and on this side or that side. And second is, if P lies on equatorial. P lies on equatorial line. Now P lies on equatorial line is very simple. That if it lies on equatorial, you know that this is minus q, this is plus q, this is the center of the dipole, and this is 2a length, and it lies here, say this point or this point. Do you know what will happen? Theta will be 90 and V is what? 0. So if point P lies on equatorial line and axial line, what will be the cases of what? The electrostatic potential due to electric dipole. So this is a very important derivation. It's a general formula. What you got it here, P cos theta by R square due to a dipole, and then the special cases of axial line and what? Equatorial line. So this is the case which we have discussed regarding what? The dipole. Now there is very important thing is, have you heard about the equipotential surface? Equipotential surface. Now what does it mean by equipotential surface? Do you know that equipotential surface, the name itself says equal potential. That means any surface which has equal potential at all the points, then that surface will be known as what? Equipotential surface. So equipotential surface you can define as any surface that has same electric potential at every point on it is called equipotential surface. Simple. Same potential, equipotential surface. I can give you an example that if you have a surface like this type of surface, and if there's a wire and you have connected it somewhere and 10 volt is the potential supplied on it. Do you know what it means? That every point there will be what? Same voltage. That doesn't mean that here it will be 9 or 1. Everywhere it will be having same voltage. So that means equipotential surface. Now equipotential surface has some characteristics. So there are 3 characteristics of equipotential surface. What are those? First, no work is done in moving any charge on equipotential surface. On equipotential surface, there is no work done. Work done is 0. Second is that electric field is perpendicular to equipotential surface. This we can also prove, equipotential surface. So that is, and the third one is two equipotential surfaces can't intersect each other. It is the same like two electric field lines can't intersect each other because there will be 2 directions of electric field. So these are the 3 points. They can be asked as a conceptual: no work done, electric field perpendicular, and 2 equipotential surfaces can't intersect each other. So equipotential surface is this. Now I am going to draw some equipotential surface, that how the equipotential surface can be drawn for the charges. Say there is a charge. Say there is a charge Q. Do you know you can draw equipotential surface for this? And we know that a charge, this is the equipotential surface for a point charge. So this is a point charge. Do you know a point charge has a nature of radial symmetry of the electric field lines. So a point charge can have equipotential surface like this. Okay. Similarly, if there's a charge of unlike nature, say this is minus Q and this is plus Q, and they're like a dipole, so their surfaces will be like this, and you can draw these surfaces, and you can draw these surfaces like this. So this is for the pair of charges opposite. That means it's for dipole. It's for point charge. You can draw equipotential surface. It's for point charge. It's for dipole. So we can draw more equipotential surfaces. Say if you want to draw for what? Any electric field lines. Electric field lines are going like this. Say they are like this. They are like this. So can we draw equipotential surface for them? Yes, we can draw it like this. So we know that there can be a plane which will be like this. So we can draw the equipotential surfaces because electric field lines are perpendicular to the surface. So this is another way. And if there are, say, 2 like charges, one is plus Q1 and plus Q2. So do you know we can draw equipotential surfaces for them is this, because point charge will have a spherical symmetry and they will be like this, and then and at the last this is what? The equipotential surfaces for 2 positive charges. So you know that this can be a question in the paper, that how to draw an equipotential surface. Work done is 0. The first concept. Why the work done is 0? Very simple. You know that on any surface, if you take a charge from A to B any charge, say Q naught. So do you know what is the work done is Q naught into what? VB minus VA. This is the potential difference. And if it's an equipotential surface, both will be same. So what is the work done is 0. So work done from A to B. So work done is 0. So this has been proved here. So work done along the equipotential surface is 0. Now, can we prove that electric field lines are perpendicular? So yes, electric field intensity is perpendicular. Electric field intensity is perpendicular to equipotential surface. Perpendicular to equipotential surface. Yes. How? We see here that simply we know that we have seen that dW is the work done, okay, in moving charge Q naught. So all of you know that dW is F dot dr, and dW is what? Q naught E dot dr, and dW by Q naught will be what? E dot dr. And how many of you know dW by Q naught will be what? dV, that is change in potential difference. And you know what is dV in any surface is 0. There is no change in potential, so this is 0, or dW is 0. So you will put 0 E dot dr. And what is E dr? So E dr cos theta will be 0. And you know E is not 0, dr is not 0. So that means cos theta is 0. So theta will be 90 degrees. So this is a general concept that E can be perpendicular to dr. So can we prove? Yes, any surface, we know that dW will be F dot dr. F is what? Q naught E dot dr. dW by Q naught is what? Change in potential. Change in potential will be what? 0. So ultimately theta can be, so on any surface electric field lines are perpendicular to the equipotential surface. So these two concepts are very important for equipotential surface. And then there's a very important thing, relation. There is a relation between field and potential. So relation between field and potential. Do you know field and potential? Electric field and potential. That means relation between E and V. There's a very famous relation. E is minus dB by dr. And that is latterly known as potential gradient. You remember gradient? Minus dB by dr. So very simple, we can calculate it. How we are going to calculate? Say there is a charge Q and there is a point, say A, and this is point V. Here say potential is VA, it is VV, and you are taking a charge Q naught from here to here at dr distance. Do you know VA is V and VV is V plus dV, we can say. So we take the charge and we know that dW is the work done. dW will be what? F dot dr. And do you know, because against electric field F is what? Q naught into E. So it is negative. So dW will be minus Q naught into E dot dr. This is, and what is dW is Q into what? dV. So minus Q naught into E dot dr. And you know this Q naught cancel out. dV will be was minus E dr. What? E dr, and then it will be what? E will be what? Minus dV by what? dr. So this can be written as like this. E is minus dV by dr. And this is E minus dV by dr is actually the potential gradient. We can say that this is potential gradient. So again repeating, dW is F dot dr, and F dot dr will be written as what? Minus Q naught E dot dr, and then this is the change in the potential, that is VB minus VA. This is dB, and this can be written as what? dV by dr. And potential gradient, and you know that if you want to write it in magnitude, it can be written as dB by dr. So this is very important relation between field and potential. And do you know, E minus dV by dr, you can see that if E is minus dB by dr, and if I say V is constant, then can you tell me what is E? Electric field 0. So here there is a very important concept. V is not 0, but E is 0. And I will give you an example of a surface. This is a charged surface, charged spherical cell. And very interesting thing is that if I ask you what is the electric field at this point, remember it was 0, you remember it. But do you know what is V? If the charge is Q, it is KQ by R. So here it proves that V is not 0, but E is 0. That means electric field is what? Discontinuous, if we can say. And potential is continuous. So this can be a conceptual question. Potential is continuous. So this is how we say that this concept can be applied for the potential gradient. So this is the concept for the electrostatic potential and capacitance. And thank you, and regularly watch my videos.